In this segment, we'll introduce the concept of magnetic flux, really based by analogy with what we've done electrically. Remember that we had found for the electric field that the concept of electric flux was very useful. And remember, the electric flux, I usually wrote it like this, a capital Phi, sub E to remind me it's electrical, uh, and this S here is the surface that it goes through. It is really by definition the integral over the surface of E vector dot dA, where dA is the area vector associated with that surface. And what this quantity does is that it in effect counts the number of field lines that cut through a given surface, a piece of surface. And generally, we always, where it's useful anyway, this general expression can, in certain cases, be integrated, but most of the time, we have flat planar areas and uniform fields, and so we had electric field dotted into the area vector for the flux going through a planar element. Well, and we found that the flux was useful. It led to Gauss's law, and Gauss's law, in very many cases, actually, of high degrees of symmetry, it's much easier to find the electric field than doing setting up and integrating some charge distributions over space. And people thought, well, that's going to be even more useful in magnetism because you've got these crazy vector cross products and the direction. So if there was just an easier way to find the magnetic field other than using the Biot-Savart law, which you have to, you got vector cross products in it, and you always ultimately have to do an integral for it, unless you can divide things up into straight line segments, as we've seen, and you have uniform fields, which is a rare case. But what one can do is do a similar definition for the magnetic flux. And in reality, one could think of this as a planar piece, a magnetic field, nice and uniform. The normal to this surface gives me the area, so the area is the magnitude of the area vector. And for that particular case of a planar surface in a magnetic field that's uniform, then the total, uh, effectively, the total number of magnetic field lines that cut through the surface is B vector dotted into the area vector. That's the magnetic flux through the area A vector. And very similar to the expressions up here, but in this case, it's not the electric field lines that are cutting it, but is the magnetic field lines. So I indicate that with a B. And again, you can generalize that just like we did earlier. If I have a curved surface and a non-uniform field, so that's really the most general case, the magnetic flux through a small platelet up here, well, if I choose this infinitesimal area element in the surface to be small enough, well, the magnetic field over this infinitesimal is going to be effectively uniform over all of it. One has the normal perpendicular to this umbrella-like surface, and one can get the flux through this piece, the magnetic flux, just using that previous relationship above. That's B dot dA in this case, where dA vector is this area vector with that little platelet. And then to get the total number of field lines that cut through it, I just have to sum all of these up over that whole surface. So a continuous sum becomes integrals, and usually to remind myself, I usually put two integrals here and put an S to remind me that this is an integral really over a surface. Some books and some authors just put a single in there and they let you figure that out yourself. Okay? But for the general case, but it always reduces in the cases of practical interest that we'll certainly do in this course to just B dot A for flat planar pieces. Let's look at the units of magnetic flux. and I can get that from either one of these. Let's take this one. The magnetic flux is B dotted into the area. And remember, one way to write the scalar product is the magnitude of B times the magnitude of A times the cosine of the angle between the two. So there's that relationship. Now then, just take the units, look only at units. So the units of magnetic flux is going to be units of magnetic field. The units of area, cosine is dimensionless, so no units there. Areas are always in length times width, which turns into meter squared. And so the unit of magnetic flux is the Tesla meter squared, or T times meter squared. I usually just leave it in that form most of the time. To me, that's much more informative. But lots of people and lots of books use a named, this is a named unit, in honor of an early day electrodynamics physicist, Weber. This is called 1 Weber is the unit of magnetic flux, which is a Tesla meter squared. And Weber is abbreviated WB, so don't be surprised if you see that unit. I'll try to, in what I do, just use the Tesla meter squared, but we certainly have to sometimes make that conversion. Uh, so people started looking at magnetic flux and thought, well, maybe, surely, that one could get something like Gauss's law for magnetism, for the magnetic field. And in fact, you do. Remember, Gauss's law for the electric field was one way to write it, or we wrote it, was like this. But a similar thing could be done here. It turns out that it's exactly identical. That the total magnetic flux through a closed surface, Gauss's law always has a closed surface, would be equal to some constant times the total, not electric charge enclosed, but magnetic charge, if any existed. However, to our knowledge and all observations to date, there is no magnetic charge. All magnetic fields are created by moving electric charges. It's not to say that in the future you might be able to find a magnetic charge. They're sometimes called magnetic monopoles, and people do searches for these all the time. And if they ever find one, then one has a total analogy. You'd have some fundamental constant over here times the total magnetic charge that was enclosed. But since to date we haven't seen any, really just a result of experimental observation, we haven't seen any, so this side has to be 0. What that means is that there is a magnetic equivalent to Gauss's law, but it's just not very useful, certainly not useful in calculating or finding the magnetic field. So we'll have to look in a different direction.